Okay, hello everyone, and welcome to another live session from 3DOptix. Today we are going to present astronomical telescope, and Keith is going to do the job for us. So Keith, without further ado, the floor is yours. Just keep in mind that all of the features that Keith is going to show are premium features, so they're not in the free version. Some of them are in the free version, but you would see that the advanced analysis, measurement tools, and all the other advanced features are part of the premium license. So Keith, the floor is yours.
All right, thank you, Gail. Well, hello, everyone, and welcome to another 3DOptix live webinar. My name is Keith Meyers, and I'm an optical designer working with 3DOptix. So today we're going to be creating two types of astronomical telescopes using the 3DOptix web-based platform. So creating effective optical designs for these devices are going to depend on our ability to analyze important points in the system, identify where we need to place our optics, and determine system performance. We will use the 3DOptix environment to determine the best path forward for our designs during this session. So hopefully this will be beneficial to you in designing or simulating your own astronomical telescopes. Okay, so with that said, let's go ahead and start right into the project, and I hope you enjoy the webinar. Okay. So the first telescope we're going to simulate is the Keplerian telescope. So this device uses two positive lenses and creates an inverted image at the output. So this is a refractor telescope, and as such, it's going to suffer from primarily chromatic aberrations. So let's start by creating the optical system, our light sources, and detectors. So the first thing we'll do is add our light sources in. Okay. And we'll put the light source at the origin. We're going to color all the light sources different colors. Okay, so we can tell them apart as they're propagating through. So we're going to start out with 3 layout rays, and this will make more sense as we propagate the sources through the system. The source shape or the radius will be 20 millimeters. We'll use a circular source ray density pattern and a circular source shape. So we don't want any angular information because we do want these pointing down the optical axis. We'll keep all those 0. For the wavelength, we'll change this to 600 nanometers. And we'll keep the power at 1 watt. And this will be an unpolarized source. Okay, perfect. Now we are going to duplicate this twice and to create 2 different source points. I'll name this source light source 2. And we're going to angle this 1 degree. And we'll change the light to be green. We'll keep everything else the same. Okay, and then for our final light source, we'll tilt this 1.5 degrees. We'll make this light source blue. Okay, perfect. Let's go ahead and propagate the simulation, make sure we set up our light sources correctly. Okay, great. And now that we have all 3 of them set up, we're going to go up here and to view, change ray color palette, and use a defined colors. That way we can see what source we're looking at as it propagates through the system. Okay, so we are going to add the first lens in our system. So we're going to open the product catalog, and this is going to be our objective lens. It'll be the LA1301. We're just going to choose the uncoated lens for this application. So it's a 50.8 millimeter lens with a 250 millimeter focal length. We'll put this about 10 millimeters from our light sources here. Okay, and again, we change the wavelength down here. We can see the actual focal lengths, the back focal length, and the effective focal length, and the front focal length of the lens. Okay, so we'll use that a little bit later. Okay, so now that we have our objective lens here, let's go ahead and propagate the simulation. And this will create a focus somewhere over here around 250 millimeters at the focus of the mirror. Perfect. Or at the lens. Perfect. So the next thing we need to use or insert is the eyepiece lens. So we'll go back to the product catalog and we'll put in a smaller positive lens. And again, we'll use the uncoated lens type. So this is a 25.4 millimeter lens with a 50 millimeter focal length. Okay. Rename this Kepler. And for this, we'll put this at the nominal position. And the nominal position is going to be given by the focal length of the objective plus the focal length of the eyepiece. So those two focal lengths combined will be the separation of our lenses. So we have a 250 millimeter objective, focal length objective, and a 50 millimeter focal length eyepiece. So we want to move these 300 millimeters apart. Okay, perfect. Let's go ahead and propagate the simulation again. Okay, that looks good. Now, we've put it at the nominal position, but we really want to look at the actual focal lengths from the surfaces that we're using at the wavelength that we're using. So we're using 600 nanometer wavelength. So the back focal length of the objective is actually, we'll round this up to 246 millimeters. And the front focal length of our eyepiece is going to be about 50 millimeters. So that's the nominal, that's nominal what the focal length is. So that's good. So we will actually change the distance here to 296 millimeters. And this will position it at the ideal location. Propagate the simulation again, just make sure our rays do hit the lens. Okay, great. And as we can see, it's at a good nominal or ideal position, and the rays that are coming out of it are collimated. So we know we're at the right position. All right, perfect. So for the Kepler telescope, the front objective is also the entrance aperture. Now, what we need to do is find the exit aperture. And the exit aperture is going to be the location where we can place our eye, where it can see the entire field of view. So that's going to be back in this location over here, where all of the field points converge into a small waist. So what we're going to do is add a couple detectors and find that position here. Just rename these detector 1, 2, and 3. We'll put this at some nominal position here. Okay. And we will create 2 more of these detectors so we can look at a couple different places here. That one behind that one. Right, and finally, our last detector. Okay, so we got them spaced out 10 millimeters, so we can check this area over here to figure out where the exit pupil lies. Okay, so we're going to go up to the analysis portal. And we're going to change all of these to spot, incoherent, polarized. Okay. Now we could change the number of pixels that we're using, but we really just want a good measurement of the beam size at these locations. So we'll just get a rough measurement here. So we won't change the pixel size. We'll go ahead and run the analysis. And then when we're done, we're going to look at the spatial intensity pattern on the 3 detectors to figure out where that minimum spot size is. And that gives us a good approximate location for the exit pupil. Okay, great. So we'll go ahead and click on the detectors so they pop out in their own little window. So that detector did not quite render correctly. Go ahead and delete that and then just create a new one here. Okay, let's get this going again. So we just need to rerun that last detector that didn't quite render correctly. Okay, that looks much better. All right, so we'll measure the waste on these 3 detectors. Okay, let's go back to our light sources, make sure that we correctly angled them. Should be 1. It's 1.5, perfect. Okay, so we've got our light sources angled correctly. Okay, so what we want to do at this point is measure our detector's spatial intensity pattern here. And we want to find where we get the smallest pattern here. So the radius of this is 4.3. So we'll go to detector 2. Measure this as well. It's 4.6. And then detector 3. Measure this, and this is going to be a bit bigger. This is going to be 5. Okay, perfect. Now, if you are unaware of how the measurement mode works, you can always click on this little indicator here, and it'll tell you how to use this. So for the fit to circle, we click 3 times, approximately 120 degrees apart, and it'll estimate the circular size of the spatial intensity pattern. Okay, so it looks like detector 1 is where we want to put our light source. So we'll go ahead and close these out. Okay, so this is detector 1, and that was at 358. Perfect. So we'll delete the other 2 detectors, and we'll locate, and we've located our exit pupil here. And this is where we're going to want to place our eye. So we're going to have the eye relief distance from the back of the lens to the exit pupil, and we'll place our eye here so we can observe the entire field of view without having to move our eye in a 2D plane around this point. And so there's also no vignetting. Okay, great. So back out here a little. Okay, so a little bit about the angular magnification of the system. So the angular magnification of the system can be calculated as the angle in here to the objective, and then the angle out from the eyepiece. Now, to make that a little bit more clear, let's go ahead and turn off the second source at the 1 degree field angle. And our on-axis source here, so Kepler source 1 is going straight through the system. So this is a good kind of reference along the optical axis to look at the angles. So obviously we know the input angle here is 1.5 degrees because we specified that for our 3rd light source. And then our exit angle out of the eyepiece is clearly much more than 1.5 degrees. So this is a much more steep angle. What this is going to do is it is going to enter our eye. And then when your eye traces back the light rays, it's going to make this object look much bigger. So we know there's going to be some magnification here, and the output angle over the input angle will give us that magnification. Now that's a little bit difficult to calculate in some situations. So as an approximation, we can also take the focal length of our objective, which is 250 millimeters, and divide it by the focal length of our eyepiece, which is 50 millimeters. So this Keplerian telescope has an angular magnification in a paraxial kind of sense of 5 times. And again, this will create a inverted image over here that's magnified 5x. Okay. So the next thing we want to do is define our field of view. And we do this by locating the intermediate image plane here, which is where the intermediate focus is. And we place a field stop here. So what we're going to do is right-click and add user-defined object, and we're going to place an aperture here. And what this aperture is going to do is going to limit the chief rays propagating through our system, which will limit our field of view. Okay, so we'll name that field stop. It's the minimum here. Oh, and we also want a rectangular aperture for this. Okay, the minimum will be 8, maximum will be 10, and the height will be the same thing. So generally, we would want a circular aperture here, but because we're using a ray fan in one dimension here, we're just going to use a rectangular aperture for ease. Okay. So we'll put this at the nominal location of the intermediate focus, right around there. Okay. Go ahead and get this centered on the optical axis here. And just set this to 260 for an even number. Okay, so now what we want to do is we want to limit the chief ray, which would ideally be this center ray coming from the second source. Coming from the second source over here, so this would be the chief ray going through the center of the lens and hitting at the edge of this aperture here. Now what we want to do is block that ray. Before we do that, we want to extend our field out to 2 degrees. We'll re-propagate the simulation, and this will allow us to have a 2-degree field of view. Okay, so we need to move the aperture out a little bit. Move this to 0.6. Maybe a little bit more. And again, we want to block that chief ray. And this will allow us to get about 50% of the illumination at that field angle through our system. Okay, move this just a little bit more. Okay, repropagate the simulation. Okay, it's a little too much. Let's back that out a little. 6.5. Okay, great. So now we've blocked the chief ray from propagating through the system. Now, all the light from here to here, from the chief ray to the other marginal ray up here, all this light will make it through the system. So we're 50% vignetted at the 2-degree angle. So this is a good definition of our field of view. And as you can see, the one ray makes it through, so we'll have about 50% illumination at that 2-degree angle. Okay, and then we can adjust this as needed if we want to make our field of view larger or smaller. And again, this is a rectangular aperture because we're using just a 2D ray fan, but we would obviously want a circular aperture if we were propagating through all the angles here. Okay, so the last thing we want to do is we want to add our simulated eye here. The way we're going to do this is we're just going to add a paraxial lens. And we're going to put it at the location of that exit pupil. Again, this will allow us to see the entire field of view here. Let's go here. Kepler eye lens, or eye. And this was at 358. Okay, perfect, right where our detector is. We're going to go to detector 1. And we'll move this 25 millimeters from the paraxial lens. So we'll reference the detector to the paraxial lens. The Kepler eye. There we go. With that, 25 millimeters. Perfect. And for the lens, we'll right-click on the paraxial lens to change the optical settings. Make this a little bit smaller, and also make the effective focal length 25 millimeters, just for ease. Okay, great. Let's go ahead and propagate the simulation. All right. And there we go. Move the lens back just a little bit here. Okay. So we'll go ahead and look at our analysis detector for detector 1. Go ahead and rerun the analysis and look at the spots on the detector. Okay, great. Looks good. And again, you can see the on-axis and the middle field point are pretty bright, and then the off-axis point is much dimmer, again, because we're blocking that chief ray, so this should be about 50% dimmer. So that's good. Okay, the final thing we want to do to analyze our Kepler telescope is the angular resolution. So what we're going to do for that, we're actually going to make this detector a little smaller, 1 millimeter. We're going to turn off light source 3. Turn on light source 2. And then we're going to find the minimum angle that we can position this, or minimum angular separation, where we can still tell. So how many zeros do I need there? There we go. So I can still tell that they're 2 points. So we'll go up to the analysis portal and make this a little bit more higher resolution so we can determine where the points are. And what we expect is at some point, the 2 points do not have enough angular separation. They will look at like a single point on the detector. Okay, let's go ahead and click that. Okay, so this looks like we cannot resolve the 2 points. And if we click on here, we will pull up a cross section of the spatial intensity pattern. As you can see, the Y, we have a little donut in the center, but we can't really tell that there's 2 points here. So let's go ahead and change the angular separation, increase it a little bit more, and see if we can figure out where the 2 points are. Actually be able to resolve the 2 points. Okay. Let's go up to the analysis portal. And we'll go ahead and turn off the second source so we don't have to keep tracing that through. All right, we'll run the analysis again. And again, what we want to see on here is 2 points that are resolvable, and that will be our minimum resolvable angle for our light source here. Okay, still not quite there. Let's move that a little bit more. Source 2. Let's go up an order of magnitude. Okay, I may have turned off the wrong light source. Let's go ahead and turn this on again. To run the analysis. There we go. Okay, apologies. I turned off the wrong light source. Okay, so there are 2 spots here. Now these are absolutely resolvable. You can see they're clearly 2 spots, and if we click, we can see that we have 2 spots that are separated. Turn off the y-axis cross section. We can go to a couple different points, and we can see that we have 2 spots here. Okay, so let's go ahead and reduce the separation a bit, find out where our minimum resolvable angle is, or at least an approximation thereof. Okay, so we really can't tell from that angle that there's two spots there. We can kind of see just from the outline that there is, but if we were looking on an actual detector or using our eye, we wouldn't really be able to resolve that. So let's move it one more time. Change the angle. Maybe double the angular separation. Run the analysis again. And let's see if we can resolve those 2 points. Okay. All right, great. So not completely resolvable. Let's move that one more time, just a little bit more so we can kind of see the dip between the two dots. Okay, great. So that is pretty good. Now we can clearly see we have two spots. And if we look at the cross section, we can see that we have a dip between the two, that we can actually see our two spots. So this cross section gives a good idea that we can actually resolve these two spots. And just looking at the detector analysis, we can clearly see that there's two spots defined. So we can continue to go at lower resolutions to figure out what the resolution of our telescope is using this method, looking at the cross section and looking at the spatial intensity pattern. Okay. So one thing to note about the Keplerian telescope is it is a bit long, and that length is due to the addition of the focal lengths, giving the separation between these two lenses. So these are going to be longer if you have more magnification, because for magnification, you will either need a larger focal length objective lens or a smaller focal length eyepiece. So one of those two needs to be adjusted if you want greater magnification. And this usually means extending the length of your telescope. So these can get a little bit long. Okay, so now that we've designed our Keplerian telescope, we're going to move on to a Newtonian telescope. So the next telescope that we're going to simulate is the Newtonian reflector telescope. And this is going to use a single non-spherical mirror as the primary mirror, a flat turn mirror as a secondary mirror, and then an eyepiece to collimate the output. So a little different than the Kepler telescope, as we're having reflecting optics inside of it. Now, because this is a reflector telescope, it's going to be shorter and more compact because we're going to fold the path back on itself. So we don't have to add the sum of the focal lengths and use that distance between the primary mirror and the eyepiece. However, because we are using parabolic mirror, the primary aberration we're going to have to deal with is coma at the larger fields of view. So let's start again by creating our optical system. We'll start with a light source. Go up here, rename this. This a little bit farther up, so we separate it from our last light, or our last telescope. I'll change the colors for these. And we will use a large amount of rays for this one. Make the radius 80 millimeters, circular ray density pattern, and circular source shape. 600 nanometer primary wavelength, unpolarized and 1 watt still. Okay. So we are going to duplicate this 4 more times. Rename these. And these will be our off-axis field points here, or source points. So 1.5. The next one, this will be light source 3. negative 1.5. Okay. Should be light source 4. Now we're going to tilt it into X. And the final light source 5. And finally, tilt it negative 1.5 in X. Okay, so we'll pin those really quick. We want to change the color of the rays. So go to each one individually. Keep that one as red. 4. Change the green. 3, we will change to blue. And 2, we will change to yellow. There we go. Now we'll be able to tell them apart. Okay, great. Let's go ahead and propagate the simulation. All right, that looks good. Looks like everything's propagating correctly. So now we're going to add the primary mirror. So we'll right-click, add user-defined object. I'm going to go up here to type. I'm going to go to mirror. And for the subtype, we're going to use a parabolic curved mirror. So we're going to do this instead of a spherical mirror because we don't want any spherical aberration in our primary mirror. Change some of these parameters. We want a focal length of 500 millimeters, which would be 1,000 radius of curvature. And diameter will be 200. Perfect. We go up here to the 3D layout here, we can see our lens. And if we want a little more information on what we're doing, we can click on the image, and this will give us some of the pertinent information. Width or height, and diameter, and the focal length. And the coding, of course, will go on the front. So let's check the coding really quick. I have an ideal reflector here. Perfect. Go ahead and save this mirror. And we'll position it on the optical axis, 500 millimeters away. Perfect. And so this is going to match the focal length with the mirror to where our light source is. Okay, so now that we have our primary mirror, we're going to want to put in a secondary mirror. Now, the secondary mirror is going to be a flat mirror because all we want to do with the secondary mirror is reroute the light outside of the telescope optical path. So we're going to use a rectangular detector. This will be more clear why later. Start 5. We'll make this a bit larger. Maybe 100 by 100. All right, and the front surface, we do want it coated with an ideal reflector coating. Okay, perfect. There is our flat mirror. So we will position this. Position the 100 millimeters from the light source here. So that's 400 millimeters from our primary mirror. And remember, our primary mirror has a focal length of 500 millimeters. Now we do want to tilt this up because we want the light to come out of the optical system. So we can put our optics here and also where we will place our eye. Otherwise, we would reflect the light back and forth, and there would be no light coming out of the system. You wouldn't be able to use this. Okay, great. So we've got that. Let's go ahead and propagate the simulation and see where our light rays end up. Okay, so one item that I neglected is we need to turn this around 180 degrees because the front face is facing the light source, but we want it facing the primary mirror. So we'll turn that around 180 degrees. And if we propagate the simulation, we should see the light rays coming straight out. Perfect. Okay, great. So we've got all the light incident on the mirror. We've got our 5 source points here, the four off-axis field points and the on-axis field point in the center. Okay. So one thing to note, if we make the primary mirror too small, we're going to miss a lot of that light that is incident upon it, and it's just going to fall back out of the system. So as you can see, all this light out here is going to miss the mirror, and 3DOptix doesn't propagate it through. But a lot of that light is going to miss the mirror and just exit the system. So we want to appropriately size our mirror. And this is a nice little optimization problem here. We want to appropriately size the secondary mirror so that it reflects the light outside of the optical path of the telescope. But we also want to size it so it's not so large that it's taking up all the space and blocking a lot of light. Because the secondary mirror will block that light and make the image much dimmer if it gets too large. So we want a very small secondary mirror, as small as possible, to make sure that our light throughput that gets past the secondary mirror gets through the system. We get a nice bright image. So we're going to start here with this 100 by 100 millimeter square. Okay. In addition to the size of the mirror and the throughput of the light, we also need the focus to lie near or outside of the optical path of the telescope, because we are going to want to put an eyepiece here to collimate the light, and also put our eye somewhere around here so we can actually see the stars or whatever is coming through the telescopes, galaxies, planets, what have you. So we do want to make sure that the secondary mirror is at a position where we can put an eyepiece here and collimate the light. If we move the primary mirror back a bit, we'll say to 50, then we may not be able to properly position our light or our eyepiece outside of the optical path of the telescope, and we may have to occlude it here. And we don't want to do that. So we definitely want to put our secondary mirror at an appropriate place so we're able to put our eyepiece outside of the optical system. Okay. So the next thing we're going to do is we're going to click on our secondary mirror, and we're going to make the front face a detecting surface. So here we're going to do a little bit of optimization on the secondary mirror. The light sources, we'll turn off the Kepler sources here, so we don't have to trace all the light rays. We'll go ahead and do spot incoherent detector polarization. And we don't really care about the resolution. We just want good enough resolution to see where the light is hitting so we can minimize the size of our mirror. So we'll go ahead and run analysis. And we'll be able to see the light that's incident on the front face of our mirror. That's coming from the primary mirror. Okay, great. Now, as you can see, the horizontal field of view is going to be symmetric on the mirror. That's because the secondary mirror, is tilted in the vertical direction, but the horizontal will be symmetric. However, the vertical fields of view are going to hit the mirror at a different position. And this is clear if we look at the mirror itself. Obviously, the field of view, or the source point that's coming down here and reflecting up, is going to have a shorter path length than the field points that are hitting up here and reflecting up. So we're going to have to compensate for that. So we minimize the size of our secondary mirror. So let's go ahead and reduce the mirror a bit. So we had it at 100 by 100. Let's change the width first because we know that's symmetric. Go ahead and save. We'll click on the mirror. We'll make the front face a detecting surface again. Okay, we'll run the analysis, and we want to see if we can minimize the size of the lens or the secondary mirror further. Okay, that looks pretty good. The X fields of view, the plus 1.5 and minus 1.5 degree fields of view on the left and the right, look like they're almost to the edge of the flat mirror. We're not losing any light, so that's good. So we know our horizontal mirror dimensions are correct. Now we want to correct our vertical dimensions. So the first thing we'll do is resize the mirror again. And this time for the height, we'll change this to 86. Okay. And we will again make the front face a detecting surface. And we will choose spot incoherent radiance again, 200 by 200 pixels. And again, what we want to see is the top and bottom fields of view almost at the extent of our secondary mirror. Okay, that looks pretty good. And again, because we do not have a symmetric center point for a secondary mirror, because it is tilted at 45 degrees, we're going to physically move this down and look at the intensity pattern on the detector as we move this down. So instead of 100, move this down to 95. Now, what we want to see is a symmetric spot for the top and bottom source points over here on the secondary lens. So in these Newtonian reflectors, generally the secondary lens is not located in the middle because of this optical attribute here. So let's go ahead and go to secondary mirror. It's already a reflecting surface. So we'll go ahead and run the analysis again. Okay, great. All right, so that looks fantastic. It looks like we've got a little bit of margin for error on all of the corners, and all the field points, the source points are on the mirror. Now, as you can see, a rectangular mirror is not ideal for this. There's still a lot of material here that we could get rid of. So traditionally, you would use a parabolic shape, not a parabolic surface, but a parabolic shape to create this secondary mirror. As you can see, there's kind of a parabolic design to the fields of view. And this, again, minimizes the surface area of the secondary mirror so you can increase your light throughput. And that's really important because it is blocking a substantial amount of light. So we want to remove as much material as possible. Okay. So as I explained before, the primary aberration here for the Newtonian reflector is going to be coma. So we're going to want to look at that. So we'll create a new detector here. And we'll place this at the on-axis field point. $200. Okay. So again, the mirror focal length, primary mirror is 500 millimeters. I placed the flat mirror 400 millimeters away. So if I put this another 100 millimeters up, that will be 500 millimeters, and that will be generally at the focus. Let's move this back just a little bit to center it. Now we're going to make the detector a bit smaller so we can look at spot size, a little more resolution. Perfect. Okay, so go to the analysis portal. We'll turn off the secondary mirror because we just want to trace the coma detector or look at the coma detector. We'll increase the resolution a little bit so we can see the spot size. Okay, let's move this up a little or down a little more. Looks like we're not quite at the focus. And now this is just from the geometry of the flat mirror. It has some thickness, so we've got to compensate for that. Okay, that's pretty good. Let's go ahead back up to the analysis portal, run the analysis portal or run the analysis again. Okay, perfect. That is a much better spot size. Okay, so we can see the on-axis is very, very small, and this is what we would expect. Now let's look at one of the off-axis source points. So grab the mirror. And we'll move this 15.3. That should be, there we go, on the off-axis source point. There we go. Let's go back to the analysis portal, run the analysis, and what we should see is some coma at this source point because it's at a farther point in the field of view. Okay, great. And there it is. We can see we're generating coma at the outside field of view source points. So we've got the tight point here and then the blur as we go out. Okay, and again, that's to be expected. So we would just need to be aware of that as we're building our optical system and compensate as needed. Okay, great. Now, the final thing we need is an eyepiece lens for our Newtonian reflector. So we'll go ahead and open the product catalog. We'll add one more lens. Okay. So this will be a 50 millimeter diameter, 50 millimeter focal length lens. Go ahead and add to the selected, and we'll put this in place. And this will be 250. Go ahead and propagate the simulation. Okay. Move this over a little bit, again, to account for the mirror. Okay, so I placed the lens, again, 500 millimeter focal length primary mirror, 400 millimeters to the surface of the secondary mirror, 100 millimeters from the mirror to the focus, and then 50 millimeters to the lens for the adjusting for the focal length. So 50 millimeter focal length. So now we have collimated light coming from all field source point angles here. Okay, and then again, we would do the exact same thing we did for the Keplerian telescope. We would find the exit pupil location, put a few detectors there, determine that point, and that's where we would place our eye or a camera if we're using a camera for this system. Okay, so just one more note. The Kepler system, the Kepler telescope, has a magnification of 5x. So there was the 250 millimeter objective, the 50 millimeter focal length eyepiece gives us a magnification of 5. The 1000 or the 500 millimeter focal length primary lens, and then the 50 millimeter focal length eyepiece gives us a magnification of 10x. So this is actually double the magnification. And as you can see, the Newtonian reflector is not twice as long as this Newtonian reflector is not as long as the Kepler refractor telescope here. So a few design considerations to take into account. You can make them more compact with the Newtonian reflector, and then you can make them a little bit smaller for the objective and eyepiece for the Kepler. And there's many permutations of this, but there's some differences in there. And again, with the refracting telescope, you're going to have a lot of chromatic aberration that you'll have to account for. And in the Newtonian reflector, you're going to have the coma at the off-axis angles. Okay, so that's all the time I had today. So this kind of concludes our 3DOptix webinar. I want to thank everybody for joining us, navigating, getting familiar with web-based platform and the applications of creating astronomical telescopes that we reviewed. So I hope the telescope applications were helpful, and the features and tools used will give you a better understanding of the platform's capabilities. So the design file is available in the application papers, Astronomical Telescopes Design 1 and 2, that are, I believe, available right now on the 3DOptix website. And so with that said, I'll hand it back to Gil, and thank you very much, everybody.
Keith, thank you very much. As Keith mentioned, this paper and other papers are under our resources and use cases. So you can find them there, this paper, 1 and 2, the astronomical telescope, and some others. We are going to upload probably next week the recording of this session, so you will be able also to see the recording on top of the papers. Hopefully you will join our next live session. Probably it will be in 2 to 3 weeks. Thank you very much for attending, and have a great day. Bye-bye.